56 million years ago, something released more carbon into the atmosphere of this planet than all of human industry combined. It happened fast, in a few thousand years, a blink by the standards of geology. It heated the entire world. It acidified the oceans. It wiped out a third of the species living on the sea floor. And it left a chemical fingerprint locked into the rock, a fingerprint that scientists have been studying for 30 years. That fingerprint points to one kind of source above all others: burned biological matter. The same signature as fossil fuels, the same signature as industrial output. And to this day, no natural explanation fully accounts for the sheer volume of that carbon. The numbers do not add up. There is a gap in the story that 3 decades of research has never closed. In 2018, 2 scientists, one of them the director of a major NASA institute, published a formal paper asking a question that no serious institution had dared to ask out loud. If an advanced industrial civilization had existed on Earth tens of millions of years before us, would we even know? They ran the numbers. They modeled what survives deep time and what disappears. And their conclusion was devastating. We would not know. The evidence would look exactly like a natural event. It would be given a name. It would be given a date. And the question of what truly caused it would remain officially open. Then they looked at the geological record. And there it was, an event with a name, a date, and an open question that 30 years of study has not been able to close. This is not mythology. This is not speculation. This is the data. To understand what these 2 scientists actually did, you have to start with the paper itself, because it is one of the strangest documents in modern science. In 2018, Gavin Schmidt, the director of NASA's Goddard Institute for Space Studies, one of the most respected climate scientists alive, teamed up with Adam Frank, an astrophysicist at the University of Rochester. Together, they published a study in the International Journal of Astrobiology. Its title was a question: would it be possible to detect an industrial civilization in the geological record? They called it the Silurian Hypothesis, borrowing the name from an old episode of Doctor Who about a reptilian race that ruled the Earth before humanity. The name was a deliberate wink, a way of admitting how speculative the question sounds, while treating the actual physics with total seriousness. And this is the crucial thing to understand. Schmidt and Frank were not claiming that a previous civilization existed. They had no fossil, no artifact, no smoking gun. What they were doing was more disciplined, and in a way more disturbing than that. They were asking a precise engineering question. If a civilization like ours had risen tens of millions of years ago, built cities, burned fuel, industrialized a planet, and then vanished, what would be left of it today? And could we tell the difference between its footprint and a natural event? To answer that, they had to run a thought experiment, and it is one you can run yourself. Take everything humanity has ever built, every city on every continent, every road, every bridge, every dam, every skyscraper, every power plant, every mine, every landfill, every factory, every ship, every plastic bottle in every ocean. The entire physical output of 8 billion people across 2 centuries of industry, stacked on top of 300,000 years of human existence. Now walk away, leave it alone, let physics do what physics does, and come back in 50 million years to look for what remains. The answer is almost nothing. And the specific way it becomes almost nothing is the whole point. Start with the buildings. A skyscraper of steel and reinforced concrete begins to fail the moment maintenance stops. Within decades, water cracks the concrete and rusts the steel inside it. Within centuries, it collapses under its own weight. Within a few thousand years, the rubble is buried and overgrown. Within tens of thousands of years, the steel has completely oxidized and the concrete has chemically decomposed. What remains is a lens of chemically unusual soil, enriched in a bit of iron, some calcium, some aluminum, with no shape, no geometry, nothing to tell a future geologist that anything was ever deliberately built there. A city the size of New York becomes a thin, anomalous smear in a single layer of compressed sediment. Now the things we think of as permanent. Plastic. We imagine it lasting forever. It will not. Ultraviolet light and microbes break the polymer chains, and within a few 100,000 years, the plastics are gone, reduced to faint traces of unusual carbon compounds in the rock. A geochemist might detect them. They would never be recognized as bottles or bags. Metals, copper, lead, the rare earth elements we concentrate by the megaton, can persist as unusual concentrations in sediment for millions of years. But without any surviving structure attached to them, they look exactly like natural mineral deposits, the kind the Earth produces on its own through volcanoes and hot springs. A future geologist would need a very specific reason to suspect that an enrichment of rare earths in a 50-million-year-old layer came from a factory rather than a vent, and nothing in the chemistry alone would ever hand them that reason. Even our nuclear signature fades. It sounds like the one thing that should last. We split the atom. Surely that leaves a permanent mark. But the byproducts decay. Plutonium-239 has a half-life of around 24,000 years. After 50 million years, even the longest-lived fission products have decayed to levels almost impossible to separate from natural background. And nature muddies the water further because nature has run its own nuclear reactors. There is a site in Gabon in West Africa where uranium deposits went critical and sustained a natural chain reaction on their own, roughly 2 billion years ago. So even a strange isotope ratio in ancient rock does not automatically mean technology. It might just mean the Earth being the Earth. So, what actually survives 50 million years in a form you can unambiguously read? One thing: chemistry, the isotopic composition of carbon locked into ocean rock. That is the single message deep time cannot erase. And it is exactly where this story turns. Because to read that message, you need to understand one simple fact about carbon. Just one. And the rest follows automatically. Carbon comes in two stable forms. Two isotopes that differ by the weight of a single neutron. Carbon-12, the lighter one. Carbon-13, the heavier one. Both exist everywhere carbon exists, but the ratio between them is not the same everywhere. And that ratio is the key to reading the history of this planet. Life prefers the lighter isotope. Every plant, every animal, every bacterium preferentially pulls carbon-12 into its body. So anything that was once alive, wood, peat, coal, oil, natural gas, carries a distinctive signature. It is enriched in light carbon. Volcanic carbon, by contrast, comes from deep inside the Earth. It has never been touched by biology, and it carries a heavier signature. These two fingerprints are as different as two blood types. You cannot confuse one for the other. And that means that when a flood of carbon enters the atmosphere and gets recorded in the rock, you can look at it 50 million years later and ask, was this biological or was this geological? Was it once alive Or did it come from the deep Earth? Which brings us, finally, to the event itself. It is called the Paleocene-Eocene Thermal Maximum, the PETM. It sits in the geological record, roughly 56 million years ago, recorded in ocean sediment, sampled from every major ocean basin on Earth. And its basic facts are not in dispute. It is one of the most thoroughly studied events in the history of climate science. Between 3 and 7 trillion tons of carbon entered the atmosphere over a few thousand years. Global temperatures rose by 5 to 8 degrees Celsius. The deep ocean turned acidic. A third of all the species living on the seafloor went extinct, and the planet took roughly 200,000 years to recover, a span of time longer than our entire species has existed. Whatever caused the PETM pushed the Earth's climate so far past its balance point that it took longer than the whole history of Homo sapiens for the system to settle again. Picture the world it made. The poles were ice-free. Crocodile relatives basked in swamps near the Arctic Circle. The tropics ran so hot that parts of the ocean's surface may have approached the temperature of a warm bath. In the deep sea, where cold, oxygen-rich water normally sustains a whole hidden ecosystem, the water warmed and soured, and the tiny shelled creatures living in the sediment died off in a wave that shows up in cores all over the planet. It was not the largest extinction in Earth's history, but it was one of the fastest and most global climate lurches the planet has ever recorded. And it is the closest thing in the deep past to what an industrial spike in carbon would actually do to a world. And how do we know all of this in such detail 56 million years later? Because those shelled creatures were keeping the record for us. Marine organisms build their shells from carbon dissolved in seawater, and the isotope ratio of that carbon gets locked into the shell. When they die and settle on the sea floor, layer upon layer, they preserve a running chemical diary of the ocean they lived in. Drill a core into that seabed. Run the samples through a mass spectrometer, and you can read the diary line by line. And right at the PETM boundary, the line lurches toward light carbon and stays there. The same signal in the same place in every ocean. And here is the part that matters. The carbon that caused it has the biological fingerprint, light carbon, an organic source. Every measurement, from cores drilled in the Atlantic, the Pacific, the Indian, and the Southern Ocean, across 30 years of research, confirms it. It is one of the clearest, most replicated signals in the entire geological record. It is not ambiguous. It is not up for debate. The carbon that triggered one of the most severe climate disruptions in 66 million years has the chemical signature of burned or decomposed biological material, not volcanic rock, something that was once alive. So the obvious question, the one the textbooks handle very carefully, is this: what biological source on Earth was large enough to dump 3 to 7 trillion tons of light carbon into the atmosphere in a few thousand years? There are 3 standard candidates, and it is worth watching each of them fall short. The first is volcanoes. Around the time of the PETM, a vast volcanic province was erupting in the North Atlantic as Greenland and Europe tore apart. Huge, sustained eruptions. But volcanic carbon carries the heavy fingerprint, the wrong one. Volcanism almost certainly helped warm the climate, but it cannot be the source of the light carbon that defines the event. The second is methane hydrate. Vast reserves of frozen methane locked in the sea floor. Its carbon is biological, so the fingerprint matches and it can release fast. This is almost certainly part of the answer. But when scientists model how much methane could actually have come out of the known reservoirs, they come up short. The numbers don't reach 3 to 7 trillion tons. The third is the cooking of organic-rich sediments by volcanic heat, which also produces light carbon. It contributes, but it too fails to close the gap. Add up every known natural source, volcanoes, methane, cooked sediments, and the total still falls short of what the rock records. The volume of light carbon in the geological record exceeds what all the natural mechanisms combined can produce. This shortfall has been sitting in the published literature for decades. It is not hidden. It is not fringe. It is a recognized gap in the explanation of one of the most studied events in Earth's history. 30 years of research, thousands of papers, and the books do not balance. Scientists describe this gap in the careful, deflating language of the field. They write about additional carbon sources that have not been fully identified. They note that the models are sensitive to assumptions about initial conditions and feedbacks. They are not being evasive. They are being honest about the limits of what they can currently explain. But strip away the technical caution, and what is left is a simple, startling admission. The single largest, most biologically fingerprinted carbon spike in 66 million years of Earth history has a source that we cannot fully account for. We know it was once alive. We know there was an enormous amount of it. We know it hit the atmosphere fast. And when we tally up every natural way to produce it, we run out of carbon before we run out of event. Now put the two things side by side. On one side, you have Schmidt and Frank, telling you that a vanished industrial civilization would not show up in the record as a civilization. It would show up as a geochemical event, a sudden pulse of light carbon, global, rapid, biological in origin, in a volume that natural sources struggle to fully explain. It would get a name and a date, and the question of its ultimate cause would stay quietly open. On the other side, you have the PETM, a sudden pulse of light carbon, global, rapid, biological in origin, in a volume that natural sources cannot fully explain, with a name, a date, and a gap that 30 years of research has never closed. Schmidt and Frank were not writing about the PETM, but what they described is a precise match for what the PETM data shows. Two independent lines of peer-reviewed science. One says, we would not be able to tell the difference between a lost civilization's footprint and a natural carbon event. The other hands us a natural carbon event, whose footprint has a gap no natural explanation has closed, and almost nobody in the scientific mainstream has ever put those two observations in the same sentence. And there is one more detail that should make the hair stand up on your neck. We know exactly what that fingerprint looks like, because we are making one right now. 150 years of burning coal, oil, and gas has released something like 500 billion tons of light carbon into the atmosphere. That carbon is being absorbed by the oceans. It is being built into the shells of marine organisms. It is settling onto the sea floor in sediment that will one day be stone. The isotopic signature of our own industrial civilization is being written into the geological record at this very moment. In 50 million years, it will be there. A thin band of light carbon, anomalous, rapid, biological, in a volume that future researchers may or may not be able to fully account for with the natural mechanisms in their models. We are creating our own PETM. We are writing the exact same entry into the exact same record. And we happen to have instruments precise enough to watch ourselves do it in real time. Think about how strange that is. We discovered the PETM by reading a spike of light carbon in the rock and asking what could have made it. And we are, at this exact moment, laying down a spike of light carbon in the rock that a future geologist will find and ask the same question about. If our civilization ended tomorrow and something dug up our layer 50 million years from now, they would see precisely what we see when we look at the PETM, a sudden global biological carbon pulse with a warming spike attached and a mass die-off in the oceans. They would give it a name. They would argue about the exact cause. And unless they already knew to look for us, an industrial civilization is not the first answer they would reach for. It might not be an answer they would reach for at all. And the most unsettling realization is not that we are doing it. It is that something may have done it before. So what happened after Schmidt and Frank published the Silurian Hypothesis? Given how extraordinary the question is, you would expect a storm of research, teams forming, models running, the scientific community doing what it does best, trying to prove it wrong. What actually happened was almost nothing. The paper came out, it got some press. There was a flurry of public interest, and then the field moved on. No follow-up studies, no funded programs, no teams formed to test the hypothesis against the specific anomalies of the PETM or any other event. Years of near silence from the institutions best positioned to pursue it. And that silence is worth examining, because it is not the silence of a question that was tested and rejected. When a credentialed scientist publishes a novel idea, the normal response is that other scientists attack it. They try to break it. That adversarial process is how bad ideas die and good ideas survive. But no one wrote the rebuttal. If the Silurian hypothesis were obviously wrong, tearing it down would have been easy and professionally rewarding. That paper was never written either. What the silence tells you is not that the question is wrong. It tells you the question is dangerous, professionally, because the incentives in science are brutally asymmetric. If you chase this idea and you are wrong, you become the scientist who went looking for ancient aliens in the rocks. No amount of rigor protects you from that label once it sticks. Your credibility never fully recovers. But if you stay quiet, nothing happens to you at all. You keep publishing, you keep your funding, you keep advancing. The cost of asking the question is paid entirely by the person who asks it. The cost of not asking is spread invisibly across the whole field, where no one feels it. And so the question was not rejected, it was abandoned. And there is a world of difference between an idea that has been tested and found wanting, and an idea that no one was willing to test in the first place. And here is the number that makes that abandonment so hard to justify. The Earth has been home to complex multicellular life for something like 600 million years. Modern humans have existed for about 300,000. Our industrial civilization, the thing capable of leaving that carbon signal, has existed for roughly 200 years. 200 years against 600 million. Our entire industrial footprint occupies about 1 part in 3 million of the time complex life has thrived on this planet. Now ask the question no institution has formally answered. What is the probability that in 600 million years, on a world drenched in liquid water and organic chemistry, through multiple mass extinctions that repeatedly wiped the slate clean and opened brand new evolutionary paths across millions upon millions of species, we are the first and only one ever to reach industrial scale? Notice that this is a far lower bar than intelligence. It does not require radio telescopes or poetry. It requires only the biological capacity to dig up stored energy and burn it fast enough to leave a mark in the rock. And we are asked to believe that in 600 million years, on a planet perfectly suited to life, that happened exactly once. And consider how much room there was for it to happen. The dinosaurs alone ruled this planet for something like 165 million years, a reign nearly 1,000 times longer than our entire species has existed so far. Whole dynasties of complex, large-brained animals rose and fell in that time. The record is broken again and again by mass extinctions. The Great Dying at the end of the Permian, the asteroid that ended the dinosaurs, and each time, the survivors radiated outward into a wiped clean world and evolved in directions nothing before them had taken. Every one of those chapters was a fresh roll of the dice on a living world. We tend to assume that because it took this particular planet this long to produce us, industry is a near miracle that could only have happened at the very end. But that is an assumption, not a finding. It is entirely possible that the dice came up civilization before, in a chapter that ended so long ago, and was recycled so thoroughly by the planet that the only thing left of it is a smudge of light carbon we have mistaken for a natural event. The honest answer is that we do not know. We cannot prove something was here before us, but we also cannot prove that it wasn't, and those two positions are not equal. One of them is comfortable. The other forces us to rethink our entire place in the history of this planet, and we have quietly chosen the comfortable one. Not because the evidence demands it, but because the absence of evidence in a record we now know cannot preserve the relevant evidence has been treated as if it settles the matter. It does not. The record is not clean. The record is blind. And what we cannot see is not the same as what was never there. Line up the facts one last time. The fingerprint sits in the rock. Light carbon, global, biological, 56 million years old. The gap sits in the literature, a volume of carbon that no natural source has ever fully explained. And the framework that connects them sits in a peer-reviewed journal, with a handful of citations and years of silence around it. Something left that fingerprint in the stone 56 million years ago, at a time when this planet had already been habitable for complex life for hundreds of millions of years. We know what the fingerprint looks like. We are pressing an identical one into the rock ourselves right now, and we do not know, we may never know, what made the first one. Maybe it was methane. Maybe it was some natural process we haven't yet modeled correctly, and the gap will close, and the story will end quietly the way most scientific stories do. But maybe the reason the numbers have never quite added up is that we have been looking for a natural source to explain something that was not entirely natural. And maybe the only reason that possibility sounds absurd is that we have decided in advance that we must have been the first. The rock does not care what we decided. It just keeps its record, patient, chemical, and blind to everything except what was once alive. Subscribe to the Cosmic Deep for more of the stories nobody tells you, from the surface of hell to the edge of the universe.